So what happened today? How come so few students? The assignment, maybe everybody can type. Okay, good. Nevertheless, we'll start the class. We'll start the recording. And so midterm will be next week, same time, same on. It'll be online on Discord, so you can take the midterm here or anywhere else where you have steady net connection. I posted the sample midterm, so you can have a look to see what kind of questions they are. Since it is open book and open internet, that means that I'm definitely not going to ask you questions that like definition questions, like what are homogeneous coordinates, or show the matrix for the Sobel edge detector, because you could easily look that up on Google. So I assume that you have access to Google. So my philosophy is that for any computational process, there's basically three components. There's the input, there's the algorithm, and there's the output. And usually I will give you two of those, and you have to figure out what the third one is. So the simplest version of that would be, here's an input image, what will be the output of the Haar feature detector using these parameter values, right? The second one, which is often more interesting, is here's the output of that algorithm, can you figure out what the input looked like? Or here's the edge map, generate a input image that will result in exactly this output of the Sobel edge detector. And the third one is I give you the input and the output, and then I ask you what the algorithm was. That's sort of the general idea for my questions. You will have to do quite a bit of programming, so make sure that your programming environment is set up wherever you plan to take the exam, and then have a look at the sample questions. Then there should be no problem. So today I want to talk about the histogram of oriented gradient feature detector, the HOT feature detector. Now, we looked at different algorithms so far, and because of the highly noisy feature, or because the fact that it's very noisy, color detection is a very difficult problem. So if we want to look at features, we looked at gradients and different ways to map gradients, calculate them. Given the various gradients, then we looked at corner detectors. And there's more advanced algorithms for detecting feature points like SIFT features, SURF features, ORB features that are based on top of it. But today I want to look at sort of area-based gradient detection, or gradient methods that use the gradients in an area in quite a clever way, and allow us to do fairly complex, fairly interesting detection. Now, the original image that I used, the original problem that I used was one that we used for our Thormang robot. One of the goals that we have is to win the Olympic gold medal in archery. If you want to do that, one of the things is you need to, with very high precision, detect the target, right? Otherwise, you don't know what to shoot at. So the feature detector, we use the Hawk feature detector in order to detect our archery target. But that's a little bit boring and not the best application of Hawk feature detector. So I'm trying to think if we can come up with some application that's a little bit more interesting. Now, the problem is that for the Hawk feature detector, there's a machine learning step involved, which means that we need to generate at least a little bit of training data to show how the method works. And so let me think what we could do. I'm wondering if I could use ChatGPT for this. That would be my dream, I guess. So then I can use that. So let me see. So I think Bing now can create images. So we did say now. Anybody translate, please? Oh, unable to read. High demand. So let's try. Where's your prompt? So let's give it a minute. I guess I'll start over. See what images we get. Need a fast car. So where's the image now? Otherwise, let's see what Google can find for us. instead of a front view, side view that I wanted to give me a front view. So now I also want a front view. Drop. So that would have been faster with Google, I guess. Now we want to save. And that is weird. That's almost the same picture. But I asked some. Now he's holding a phone. One of them. I want all of them to hold the phone. And here the same. Okay, so now I have 3 pictures of people walking and holding a phone. And now, let's see what stable diffusion did. Now there's 2 of them holding the phone. Okay. Obviously my AI prompt skills aren't good enough to get that to work, but it's okay. We can use let's switch to English. So which one is settings? Alright, where is the settings menu on Krita? Can you tell me? I need to switch it to English. How do I switch it to English? So I need settings and then language. So on here there ought to be a settings menu. Come up front and have a look, and then just tell me which one it is. settings. Maybe. And then there should be language. No, I think that was actually probably correct. Oh, these are themes. Oh, keyboard, yeah, we try the keyboard. Oh, that's the menu. Ah, there. Okay. Good. Let's close it. Okay, thank you. So now we want a new say width 256 by 8 would be 2040 and height 256 512. 156 by 256. So that'll make it look a little bit weird, but we'll use that. We can copy that. Paste it here. Then we'll get the next one. So we have 5 pictures now registered to the same size of people walking. And now phone. Do these guys? Screenshots. Here's our first image. There's something to work. Should have used scale. That's why. Surprised that this was broken. Then phone 2. And phone 3. Okay, how come? Opens up those. Okay, so now we have phone 1, 2, and 3, all scale, and we need to copy those. And then we have walking 1, 2, 3, 4, 5. So let's see, let me try and get those images. Oh. forgot that I did that already. Walking 2, then walking 3. Walking 4. And walking 5. And then we have 3 foam ones. Now this is very small, the training set, of course. So our results. What would you expect with a too small training set? Should your results be better or worse? When you run it and you run your validation, then usually it will end up being better because you are only looking at a very small part of the data set, and there's often something that the algorithm will latch onto. even if you use testing and validation correctly. But the generalization ability of your algorithm is going to be very poor, which means that outside of your training set, it will act very poorly. So if you probably will get the accuracy to be extremely high, but if you then point it on a street scene in Taipei and expect it to count pedestrians, then it will not work very well because it doesn't have enough data to generalize correctly. So, form 3. Okay, so we loaded them all in. So now I also had another image before. That's what I actually wanted to generate. But let's have a look at our problem, and then we'll see the original image values. So I had a stream of pictures like that of people walking, so we can add the other ones now into that data set. So one of the questions is what are we going to do if we have a more complex computer vision problem where we need to define and describe a shape that is much more variable than an edge or a corner, for example. So one of the crucial features that you need, especially if you're building self-driving cars, for example, you need to be able to detect people. So here we're looking at a problem for detecting people, but this could also be other kinds of shapes that we need to extract that are not just a template, like where parts of the shape are moving. Like the problem with detecting people is that your arms swing while you walk, your legs are moving, so it isn't just one template that we need to be able to match. Right? The tricky part is that you're really looking at a shape that is constantly changing. So similarly would be medical imaging. Shapes of arms and legs of people are not always the same. They have different poses when the x-rays are taken and things like that. If you want to correct for that and register the image properly, then that will be problematic as well. So here is our image, and of course there's other problems, like here the lady is carrying, I don't know what that is, guitar probably, or a baby, so that's going to make the detection even harder. So let's see how we can attack that particular problem. Also color, because they can wear green clothes or black clothes or white clothes, so there's no color predicate that you could define. Right? Or dress, yes. So now I extracted some people from that set, and we have a couple of samples now, just so that you can see what that looks like. I can also add in my other pictures. Then I need to just posted on the Discord a link to the Jupyter notebook. These notes I don't need. Okay, so sample of people walking, and now since colors and intensity levels are not really indicative of anything in that particular domain, they may be wearing black clothes, white clothes. We need to use the gradient somehow in order to be able to extract them from the background. But more importantly, then we need to use the gradient in order to match the image to one of the two classes. In this case, I use walking people, people that are walking, or people that are walking and talking on the phone. Or I think I use walking people and people that are sitting down. So first here, I calculate the gradient of the image, just to be able to show it. Now, one trick, if you do need the gradient of an image, one fast way of calculating it is you can calculate the Sobel edge detection output in X and Y direction, and then take those numbers and convert them to polar coordinates. Because the polar coordinates, that would be then the direction and angle of your gradient. So here I just go through and I print out the direction and the magnitude of the gradient. Oh, this is... This is just the routine to calculate the gradient. Here is where I actually calculate it. And then here we can show the output. So now I subsample, I didn't plot the gradient for every pixel. I just subsampled it every 8 pixels. And then this is sort of what we get. You can see on the leg here where I managed to hit the gradient, right, where I managed to hit the edge just by accident or by chance. We do get a very nice direction and a high magnitude along the legs. The arms here, not so much. Same thing here. So now let me actually try, and what do you think will happen if I increase the kernel size here for instead of 3. Let's say I want to set it to a much larger number. Let's say I change it to 11. Then what do you expect to happen with your gradient image? So we just run through the same processing. Now I get many more gradients, right? Which makes sense because if I have a larger mask, then the more pixels are going to have an impact. So for example here, if it's only 3 by 3 and I'm 3 pixels away from the leg, it's going to show no gradient because it'll only look at the background. If I say 11, now there's the gradient from the leg. Even though it's weighted less, it's still going to show up in that particular pixel. So you're going to have a gradient that sort of bleeds out more. So let's set it to 5. When we actually calculate the histogram of oriented gradients, we use the gradient for every pixel. So in that case, the mask doesn't really matter that much. So here, we get a couple more gradients. So if I want to use that as a pattern in order to detect a person walking, then what could we do? Well, the first idea may be to say, okay, I just take every pixel that we have, similar to what we do here, and I turn this into a feature vector, which is basically what a neural network would do, right? That would be the input layer in a neural network. And you would say that, okay, here there's no gradient, so I just record the magnitude of the gradient. So 0, 0, 0, 0, then there's 1 here, so maybe 5, 0, 0, 0, 0, 0, 0, then here's a very high one, 100, then there's a couple of, this one is maybe 30, and then another 100, so on and so forth. Or you can encode both, not just the magnitude of the gradient, but also the direction of the gradient, and then say, okay, this is an example of a person walking. And then the hope would be that that vector would be similar for the other people that are walking. So you get similar gradient vectors. You could calculate some kind of similarity measure between the vectors, and then see which one it best matches. But that approach is not going to work because, for one thing, if I have a particular vector here, like 0, 0, 0, 0, and then the head 10, 20, for example, right? If now the person is shifted a little bit to the right, then instead of having 0, 0, 0, I have more zeros because the head doesn't show up until here. So the whole vector is going to be shifted. And not just that, it's also then the offset within the row is going to change. Right? Similarly, if the person is shifted to the left instead of 0, I may have the head right there, which would introduce a large gradient in the first couple of cells already. So the problem is that that kind of feature vector would be not translation invariant. If I move the figure, the vector numbers, the numbers in the vector are going to change a lot. And we don't want that, because if it's the same person, it should come up with the same vector description, right? Because you want to be able to match them. So if it's exactly the same image, you just shift it a little bit or rotate it a little bit, then it should give you the same response. If it gives you a very different response, it is not a reasonable pattern to match. So that's problematic. So now let's see what else we can do in order to develop a more robust feature descriptor. So the idea for histogram-oriented gradients is that we accumulate nearby gradients into a single descriptor. So this was done by Dalal and Triggs, and the POC feature detector has proven quite powerful in detecting complex shapes. In particular, pedestrian detection is one of the first applications. So what we do is we take our image and break it down into squares. The size of the squares is 16. So 16 by 16 pixel buckets. And we show the gradient there. We calculate the gradient in there. So here it's the areas that I'm interested in right now. So I decide to break that shape up into 16 by 16 pixel blocks. And then I want to use some information about the gradient in these blocks and the relative position of these blocks in order to describe the shape. Now we're dealing with angles, and angles are always can be tricky in a computer program because they have this nasty habit of wrapping around at 360. So minus 3 degree is the same as 357 degrees or 709 degrees. So if you try to calculate the difference between angles and things like that, you have to be careful. So one good habit to have when dealing with angles is to normalize them while you do your computation. So you can always map them to be between 0 and 360 degrees, or since we're dealing with angles, the other problem is that most of the computer libraries use radians, but some libraries expect angles in degrees. so that can lead to vastly wrong results too. So here I just mapped the angles to be between minus 180 and 180 degrees, and that's that's a good routine to have. Or if you prefer between 0 and 360, you can do that too, of course. Here I map it because we actually modify the angle to be between 0 and 180 later on in this particular algorithm. So the histogram of oriented gradient algorithm works by calculating the histogram of the gradient angles in each square. So we want to have a descriptor, we want to know what that picture looks like with its gradient information. Since we need to, I guess that's an interesting discussion to be had now. We're trying to match images, right? And at the heart of that problem is actually anytime you're trying to come up with a system that can generalize, that can correctly classify images that it hasn't seen before, that can make predictions, like a classifier. Anytime you're trying to do that, what you must do is you need to take your input data and somehow you need to compress it. You need to compress it to the relevant features, and you need to get rid of all the irrelevant features. That's any classifier, you have to do that. So we want to throw away here, for example, I have a lot of data, right? I could use every number here, 0, 0, 0, 0. I could use all of these zeros, and all I would be doing is mapping exactly the background. And then, if the person just moves its arm by a tiny little bit, then a lot of those zeros are going to be changed to a 1, to a black pixel. Right? However, for making a distinction between a pedestrian and not a pedestrian, that difference is not relevant. If somebody is walking and they move their elbow a little bit left or a little bit right, it should still come out as, it still must match a walking person. So if you want to have exactness of the match, then we have another technology that is really good at doing that. That would be a database. If you need to find exactly that picture, then that's not a problem. You can store it in a database and then come up with some SQL code to extract it, to retrieve it. So that part is easy. From an AI point of view. What we need to do is we need to extract the relevant features, which means that all the data that we have, somehow we need to compress it into something, and the compression has to be in such a way that the parts that are important are still there, and the parts that are not important are thrown away. So what happens to a signal that is compressed? Let's say I transmit this picture to you, right, as a stream of bits. And and then you would get like 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 0, so on and so forth. So you get that stream, right? If I compress the data and I send it again, then instead of the original idea of compression, of course, was to make like a compression into JPEG, for example. I would make the image smaller, right? The whole idea of compression was to reduce the size of the message that I need to send in order to transmit this data. So now compression, from that point of view, from a data scientist, communication scientist point of view, data science is all about reducing the size of the message. In order to be able to reduce the size of the message, you have to be able to predict what the bits are going to be, right? Because if I send you 0, 0, 0, 0, 0, the whole idea of data compression would be that if I send you 0, 0, 0, 0, 0, 0, 1, then 0, 0, 0, 0, 0, 0, then what do you think the next bit is going to be? You would also think that's a 0, right? If you get that stream long enough. Now, information theory actually has a way of measuring this randomness in the stream. That's called entropy. And compression tries to increase the entropy in the message. It's trying to make the message more random, right? Because after compression, the signal that you get will look more random. It'll have higher entropy. So what's kind of neat is to think about this and relate it to classifiers and machine learning, because if you consider it from that perspective, then if you are really, really good at AI, and there have been some people have done tests with ChatGPT-4. Just 2 weeks ago, there was a study that was published that actually showed that ChatGPT-4 can compress text, English text, better than the best compression algorithms that we had for text before. Now, text is not is different from image compression. Image compression we usually allow for a lossy compression, right? Some of the pixels are changed. We won't be able to reconstruct. If you take a photo and then you apply JPEG compression and then you decompress the image, the output is not going to be exactly what matches the input. But for text compression, we don't want to accept that. So that's why it's a slightly different version. So it's a lossless compression. But anyway, as we get better and better, the compressed text will look more and more random, right? And the better your AI is, the more random your output is going to look to an observer that does not have the decompression algorithm. So if you think about that and you lead it to your logical conclusion, that would be that if you truly understand the text, your output message should be completely random, right? Then you can send it to the decompression algorithm, you will get your original text back. So if you can do that, then you could also just feed random data into your decompressor, into your decompression algorithm. And then what should the output be? If logically what should follow is that the output of that should be some really good book, right? It's like one of the books of Shakespeare that Shakespeare would have written if he had enough time, but he didn't. But you learned the compression on Shakespeare text, you feed in random data, which is basically what the stable diffusion algorithms do, right? That's how they create images. They start with a random setting of the weights of the latent space and then run the output pipeline on that. And so we're getting pretty close to this idea now with ever more powerful deep learning architectures. But we're still a long way away from having it completely compressed. So here's the gradient information for the different log boxes. And now I want to compress the information, the gradient information in those boxes somehow. And so what we do is we calculate a histogram of the gradient angles for each one of the blue squares. So now each square I want to take those 16 by 16 numbers and actually it's a pair of numbers, right? It's a gradient, magnitude, and angle. And I want to take that data and compress it down into something smaller that still maps, allows me to detect whether somebody is walking and holding a phone, for example. Now, the gradient, whether it goes from black to white or white to black doesn't really matter, right? Because we don't know about intensity levels anyway. We don't know if the background is black or if the background is white. And we don't know if the person is wearing a white shirt or a black shirt. So that's why we can take the gradient angle and simply take it, map it to between 0 to 180 degrees. And then we take that, we discretize the angle from 0 to 180 degrees into 9 buckets, and then I sum up the angles. How many, the angle, the gradient, how many of those are arranged between, so if I have 9 buckets, then every bucket is 20 degrees wide. So if one pixel has a gradient between 0 to 20 degrees, then I add 1 in that bucket. And if it's 90 degrees, then I add 1 to bucket 5. Now, every time you do discretization, like here we take these 16 by 16 pixels, or when we're doing the buckets, when I say 9 buckets, then this is problematic because the algorithm then may be very sensitive to the boundaries that you establish. So for example, in this case here, every bucket is 20 degrees wide. So if my current gradient angle is 41 degrees, then it's going to go into bucket number, in the third bucket. If it's 39 degrees, it's going to go into bucket 2, the second bucket. So if it's 39.99999 degrees, it's going to go into bucket number 2. If it's 40.0000 degrees, it's going to go into bucket number 3. So there's a very hard boundary between those two. The Hawk algorithm alleviates that problem by blurring the cell counts afterwards. So we try to alleviate, we try to reduce the exact boundaries here in order not that I get a vastly different output if I use 41 degrees as opposed to 40 degrees, or 21 degrees as opposed to 20 degrees for my buckets. So we calculate a histogram of the gradients, group them into buckets. Each bucket is 20 degrees wide, 9 buckets in total. We will get a sharp change in the edges of at the edges of the bucket. So that's why we add the gradient not just to the bucket itself, but also to the previous bucket and the next bucket, but we weigh less. So every bucket that is within that range, we add 1 to it. So here's my histogram, just with 4 angles. So 0 to 45 degrees, 45 to 90, 90 to 135, and 135 to 180. So now I have counts of 0. So then I go through the gradients in my 16 by 16 field, and let's say I have one that's 20 degrees, and then I have one that's 45 degrees. So 20 degrees would fall into this bucket here, right? Because it's between 0 and 45. So then there would be no problem. We would write a 1 here. But the 45 degrees then matters. Is it 44.99 or 45.00? Right? So that either we add 1 here or we add 1 here. If we don't do any blurring. But in order to avoid these kind of hard edge cases, the algorithm is clever, and we weigh the angle when we add 1. Let's not make that 20, let's make that 80 degrees. So with this one here, 80 degrees, we add 1 here, but we also want to add it to the neighboring buckets, this one and this one, in order to avoid any round of errors. But I don't want to just add 1s here, because then that would just increase the count for all of them. Then I want to somehow take into consideration where the pixel is. So here, this particular pixel, the distance, I take the distance to the edge for the particular bucket. So 80 degrees, if I look at this range, it's 45 to 90, right? So 80 is here. So now I want to say, okay, this gradient could also go into the next bucket, right? And into the previous bucket, but because it's off here only 10 degrees, that distance is less than here. I want to say, oh, I want to add more weight to here and less weight over there. Right? Because it's further away. It's less likely that this actually would have been 45 degrees or lower. But if it's 80, then it's likely that maybe that angle should have been 80 degrees as opposed to, or 91 degrees as opposed to 80 degrees. So in this case, I would add the whole range, basically 10 over 45 multiplied by 1. Right? And here I would, no. And here I would add minus, so that's going to be added in this bucket there. So we try and spread out the edge gradients as we add them into the buckets. And the closer you are to the boundary, the more weight you're going to pass into the next bucket. So here we calculate the histogram of the gradients. We generate that many empty buckets, and then we go through, we normalize the angle, and I calculate both. I need the quotient and the modulo of dividing the angle by the number of buckets that I have. First one gives me the actual bucket that we're in, and the next one is the weighting for the next and previous bucket. So then we can run that, and another problem that we have there is I need to count how many pixels there are. So then we can plot the histogram outputs for our Hawk feature detector. So this is 3 parts. So for example, here we have a background pixel, so there's no gradients in any directions. This one is log 1, 3, so in this picture 1, 0, 1, 2, 3, it will be here where the face is, so there's lots of gradients in various directions. So it's rather a little bit flat there, the gradient directions. And here it would be more binomial, like it's more on the 0 and 180 degrees. Everything in here is rather low. So now I took the image, 16 by 16 pixels, so 256 pixels, 3 color channels, so 768 numbers, and I compressed it down into 9 numbers. Because right now that whole area is represented by 9 floating point numbers, which corresponds to the histogram of the gradient. So this is what I mean by compression. We went from 768 to 16 numbers. We went from 768 to 9 numbers. Now, one problem that we may have, or that we need to consider, is that the gradients, depending on the brightness in the image, the gradient values are going to go up too. Which is why we're not really so interested in the magnitude here. But still, the counts can be quite different. So we want to normalize these gradients. And sorry, I made a mistake here. We don't actually add 1. Here we add the magnitude of the gradient. But like the gradient is 2 numbers, right? It's an angle and a magnitude. So the bucket, the angle determines the bucket, but what we actually add in the bucket is not 1, but it's the actual magnitude that we add there. So we're not just counting the number of pixels that have that gradient, we also multiply it by the magnitude. So now we want to normalize it, and the normalization is to basically take this vector here. This can be interpreted, these 9 numbers can be interpreted as a 9-dimensional vector. And then we scale that to be between 0 and 1. So we just normalize the vector. So that this particular vector now has a length of 1. So now we can compare the shapes of those histograms. Because the whole point to have 9 numbers is that we can extract some kind of information about the underlying shape in that particular rectangle. So now what I can do is I can actually plot this, and it gives a fairly interesting visualization. For the ones that are above a particular threshold, I want to show it. So calculate the gradient, calculate the Hawk, normalize the Hawk, and then visualize the output. So here now is a zoomed in part of the image, and this would be the visualization. The idea is to show the histogram with respect to this 0 to 180 degree arc, and that's where I have the plots, except that so let's say if 20 degrees, 40 degrees, 60 degrees, 80 degrees, 90 degrees, 110, is it 110, 130, 150, 170, 190. If the numbers are like this, and that shows us that most of the gradient will be in the 90-degree direction. So this is what we see now zoomed in for different parts of the image. So here there's no gradient, so I mean very small ones, so it won't actually print out anything. Here, these ones are all 0, but there's some gradients in this direction. Some strong gradients in this direction. Here, some of them are going upwards, so on and so forth. So this is just for us to sort of get an idea of what the what the feature detector so far, what we actually detect. Here there's a tiny bit at 90 degrees, probably from these white areas there. And if the gradient magnitude is above a certain threshold, I just color them in red, otherwise I color them in blue. So that just shows us a little bit about the strength of the gradient here. And this is quite strong, right? It goes from there to outside of the box. So here it is over the entire image. So a little bit harder to see. And this would be our output. In a sense, this is our compression step. The entire image now is broken down into these 9 floating point numbers from the original 768. 16 by 16 blocks, 256 pixels, and then red, green, and blue for each pixel. But now what? Now I have what seems a reasonable approximation of the shape in each 16 by 16 region, right? But I need to write an algorithm that returns true or false depending on whether this is a picture of a person walking or not, right? So how is this going to help me to come up with the classifier? I need a classifier. Now, even though this hawk feature seems like a good idea, it's still not exactly reasonable, or it wouldn't be trivial to figure out what should the hawk look like for if there's a person in the image. What should it look like if there's no person in the image, right? We can see this is what it is for this picture. This is what it looks like. But if there's another person walking, then we're not sure how this is going to change. Right? What happens if it's a woman walking there? How would the histogram then change? So coming up with a classifier based on the hawk features manually would be quite difficult. So you cannot really look at those 9 floating point numbers and then say, oh yeah, that's a person, or no, that would be a person sitting. So like many other classifiers, we now use machine learning in order to take those low-level features from the hawk features and then pass them in as training data for a machine learning system, and then have the machine learning system try and figure out what the correct classifier should be. So we've done quite a bit of work for the machine learning system. We took what we thought is a reasonable approach to extract those features, and now in the last step we use a machine learning system to try and learn how to take those numbers and detect people. So we have 6 by 4 blocks, so that's 24 blocks. Each block consists of 9 numbers, so that would be 240 216. So that will be 216 numbers in order to represent the entire image. That's what we're passing into our machine learning system. So now I take some random people and I apply the hot feature detectors to it. And then I take the output of this feature detector and flatten it and convert it into a string of 6 by 4 by 9 numbers. And then that's my input, and then I add a classification saying, yes, this is a person, in order to generate my training data. So here are the 4 people that I used for my training data. And then I also have a picture of people that are sitting, and I do the same thing. So here, these are people sitting as opposed to walking. So we take 4 people that are sitting and generate training data for those, saying that they are not walking people, or people that are not walking. So we have some negative examples. Now, here you have the pictures. So now I generate the training data for X's and Y's for all the sitters and all the people that I have. And I train a classifier. In this case, I use a support vector machine, but you can also use a machine learning system, a fully connected layer, or anything else that you want. And then let's see how that works. Yeah, not too good our accuracy. Very good. Like here we are 100% correct. So that looks pretty good, right? Now it seems like we have an algorithm that can allow us to detect whether a person is sitting or walking. However, this is completely meaningless at the moment. If you want to apply that in the real world now, probably the result is not going to be very successful, because we have not done any validation tests on this at all. In particular, whether you should never use all your training data. you should never train your system on all the data that you have available. At a minimum, you need to split it into a training set and a validation set, those two. And it's quite tricky often to make sure that there's no bias introduced by the way that you select your training data and your validation data. However, that would be the topic of another lecture, different lecture here. The machine learning part is not the main focus. The main focus is on generating the Hawk feature detector and explaining the Hawk feature detector for it, or explaining how it works. So usually you want to do something like a 10-fold cross-validation. However, I only have 5 pictures, so I can only do, I couldn't do a 10-fold cross-validation because I can only remove 5 people from it. So if you wanted to apply that in practice, you would need to start with more training data to start with. So I was hoping I could use ChatGPT to generate that training data for me. Unfortunately, that is probably possible with the right prompt, but it would take too long here. So I just took those 5 people that we have. Also, another mistake that I made here is that the training data is strongly correlated. First I show all the positive examples, then I show all the negative examples. Now for support vector machines, that doesn't actually make a difference, but for many other machine learning algorithms, it can make a difference. So that's another bad idea for training regimen of your machine learning system. Another thing to keep in mind here, for example, is that sometimes when you generate your training data, you also have to be very careful. For the people sitting, there was some URL pasted into the image there, right? So that means there's some writing, some gradient in the bottom part of the image. For the walking people, there was no URL there. So if you only use that training data, given a support vector machine or a network, you don't really know what the function is that the network learned. So you have to be very careful. The system may have actually just learned on detecting walking and non-sitting people by looking to see if there's any gradient in the bottom part of the image. And of course that will fail in practice then, badly. And there's a very famous example of that. In the mid-1990s, the American military wanted to develop a neural network system. Actually, they wanted to develop a system to detect enemy tanks. In the 90s, it would be Russian tanks versus American tanks. So they want to be able to take a picture, then gives the picture to the system, and it should print out whether this is an American tank or a Russian tank. And the researchers took their training data, they went out and collected images of American tanks and Russian tanks in the field. Then they trained their system, and they, of course, knew what they were doing, so they did proper validation tests and everything. They run a tenfold cross-validation on their training data, and they were extremely confident that their system was working 99.9% accurate. It was working extremely well. So the generals who had given a lot of money to that research problem, or that research group, they wanted to see a demonstration, and they went to the big day of the demonstration, and nothing worked. The whole system was basically, the accuracy of the system was 42% or something like that, which was actually worse than just flipping a coin, right? Like you would get 50% if you just flip the coin on, you would think, if it's a fair coin. So what had gone wrong? What went wrong was that the researchers went out on Tuesday and they took pictures of the American tanks. And on Wednesday, they went out and took pictures of the Russian tanks. And on Tuesday, it was a sunny day. On Wednesday, it was a cloudy day. So what the system actually learned had nothing to do with the tanks. The only thing that it learned and why it was so good was to distinguish between a sunny day and a cloudy day, which is a much easier problem than distinguishing between Russian tanks and American tanks. Right? But the problem is, and you have to be really careful, right? Because you cannot really ask the system, what did you learn? Like if it were a rule-based system and it said, oh, if the pixels in the top part of the image are very bright, then it's an American tank, then you would know this is nonsense. This can't possibly be true, right? But for a neural network, you really don't know what it learned. So you have to be very careful in your training regimen, in the selection of your training data. Any kind of bias in the training data is going to be basically amplified in your machine learning system then. And the other thing that is interesting is this kind of problem. Of detecting the person walking. The best systems nowadays for detection of people walking are actually deep learning networks, right? And deep learning networks will take a different approach. Instead of trying to learn the classifier like this, like the hot feature detector, instead of trying to learn that, they would just feed in millions and millions of images, right, of all kinds of things, and then they would train a network. Now, 5 years ago, Richard Sutton posted a very interesting paper. So Richard Sutton is an extremely famous researcher in machine learning, and particularly reinforcement learning. He was basically the first one that made major progress in reinforcement learning algorithms. And he basically posted a paper that was titled something like "The Sad Hard Truth." And the gist of the paper was that he said that whatever humans are trying to do, like this hot feature detector, when you think about it, trying to work on that problem is actually a really clever idea, right? They put a lot of thought into coming up with the algorithm to extract that feature vector, to come up with the idea of using the gradients. And Richard Sutton said, in spite of that, the best algorithms nowadays all fare better if we let the machine learning system just start working on the actual image data. So no matter what humans think of, what kind of abstract representations here would be useful. Turns out that with enough computing power, the machine learning systems nowadays do a better job finding their own features, right? Because in a sense, your deep learning network, when you train it, it does compression as well, right? You go through smaller and smaller layer sizes, right? You compress the image that way. You have less and less neurons to get the image. So it does do a sort of it does do a compression, and it does learn these high-level features. Right? It seems like networks are doing a better job at this than humans do. I'm not convinced with this argument because we really don't know what the networks learn. So now on this millions of images on the that were used in order to train the algorithms, if you test it on these kind of images, which is what we sort of have to do, right? Then the neural network will perform better than what the feature detectors would do. However, I think that's just because even if you have millions and millions of images, you're still highly biased. Because if you scrape images of the internet, right, and you ask for pictures of the Eiffel Tower, then many people, millions of people every year take pictures of the Eiffel Tower, right? But those pictures of the Eiffel Tower are all going to look something like this, right? So whatever it is in these pictures. Now sometimes it's cloudy, sometimes it's sunny. So if you have enough training data, the system can learn that the sky, whether it's raining or cloudy or sunny, doesn't really matter. Right? But if you take now pictures that are extremely unusual, so somebody takes a picture of the Eiffel Tower and the Eiffel Tower looks like this, right? Maybe they were drunk. They had too much French wine, which of course is very nice, but they took a picture of the Eiffel Tower like that. Now you ask the system whether this is the Eiffel Tower. Pretty good chance that your learning network will not be able to recognize that. But the human ones, where we actually realize that rotation and translation, we have to be invariant of that. So that's why we came up with this whole idea of gradient angles and normalizations and things like that. It may still be able to recognize this correctly as the Eiffel Tower. Because when the human generates these features, the human will automatically rule out anything that doesn't make sense, right? You would not generate a classifier here that has anything to do with the URL in the bottom, for example, right? In fact, you'd work very hard to make sure that your classifier is insensitive to that. So if in your training data, however, URLs are somehow, and it doesn't need to be all of them have a URL and none of them on the walking people, right? There could just be a small correlation, and that may tip it over sufficiently in order to get the correct classification. So if some of them have this kind of extra artifact, then the network will latch onto it. Because for the network, it doesn't make any difference what the features are. It doesn't care about what are reasonable features and not reasonable features. And unfortunately, we cannot ask the network what features did you extract? What is the important parts of the image that you're actually looking for? So I think there's still lots of scope for human reasoning in machine learning and coming up with intermediate layers. Certainly also as validation, right? If you can show, for example, that the Hawk features somehow are similar to the kind of decisions that were made by your network, then you may have more faith because now you understand a little bit more about what the network actually does. So I think that's also valuable research, and so I'm not quite as pessimistic as Sutton, where he basically says, oh, we should just give up on all this surf features, SIF features, Hawk feature detectors, all of this is not as good as what our networks can learn by themselves. I think that's because they're exploiting spurious correlations in your training data set. And those correlations are useful for getting the value, classification accuracy high on the training data, but the real universe of data that we have to classify is always going to be the training data that we used is always going to be a tiny, tiny fraction of the possible images that we may have seen, or we may have to classify in the future. Okay, good. So that's it for today, and we'll continue next week with the midterm.